I'll begin by thanking the organizers for the opportunity to present this talk. And I guess before I begin, because of the makeup of the audience that we have here, I should just make clear from the outset that the problem that I'm going to be discussing and presenting is motivated by experiments that have been carried out in the context of superfluid helium-4. And that's the main motivation for this work. Right, now, okay, it doesn't seem to work. So let me just do it like this. Yep. Okay. Right, so whenever we are interested in understanding particular aspects of a condensed matter system, then the first thing we want to understand is the type of excitations that it can support. And so in helium, of course, people have used various techniques to understand various excitations that can exist, namely phonons, protons, and of course, vortices. And in particular, when it comes to vortices, because these objects are very difficult to visualize in superfluid helium-4, people have, experimentalists have been using various types of probes over the years to try and infer certain properties about vortices. And here I have some examples of the types of probes that have been used over the years. So typically, people have used, for example, ions, which they inject in bulk helium. And then if these ions are charged, they can drag them with an electric field. And based on the mobility of these ions in the superfluid, they can infer the type of excitations that are present because they basically dictate the drag that the ions will experience. And this was the techniques that were used, for example, to understand the scattering of excitations due to phonons and protons. But thereafter, they were also used to decorate vortices. And in the early days, they were used to study vortex arrays that were created in a rotating vessel of helium. More recent years has seen application of various of these probes, various probes at these temperatures of around 2 Kelvin, where even though the medium is superfluid, there's still a significant normal fraction present, and so normal fluid fraction. And so the vortices that they were able to decorate with hydrogen ice particles and visualize basically were highly damped and did not exhibit the complex type of excitations that are believed to arise at very low temperatures. So there are now efforts on the way in various groups. So Wei Wo's group in Florida, there's the Manchester experiments that are being carried out, where basically they are deploying other types of probes, namely excimer molecules or electrons, to decorate these vortices, and being much smaller, they can begin to infer certain properties of the vortices on the scales of the core size. So one of the nice things about using charged ions is that because they have these Coulomb interactions, then the vortices can become uniformly decorated by the ions. And so this is taken from snapshots of experiments carried out in Humphrey Maris's group at Brown University, who's been one of the main driving forces behind the studies of electrons in helium. Now, the reason we got interested in this problem is because the question is, what happens when you begin to decorate vortices in superfluid helium at very low temperatures and then begin to drag these ions through the application of an electric field? And so the setup in the Manchester experiments is they have basically this rotating cryostat, which sets up a regular vortex array. And then they inject ions onto the array. And because of the configuration of the applied electric field, these ions end up being trapped here. Now, after some time, they instantly flip the electric field, and the ions begin to propagate along these vortices. And given that we know what the distance is, we can measure the time it takes to pick up basically the first signals of current arriving, and then you can work out basically the velocity or the mobility of these ions. And so in these experiments, what they typically find is that the current has two distinctive peaks. So the first one is believed to be due to the first ions arriving that have traveled along an essentially straight vortex. As they travel, they will agitate the vortex and create excitations on it, and so any ions arriving thereafter will experience more drag due to interaction with Kelvin waves. There is also this other distinctive peak here, and that's believed to be due to the fact that occasionally you can get little loops pinching off the vortex lines, and so you end up with these charged vortex rings that travel, and their propagation velocity is well understood and has been extensively studied, and that can explain the second hump here. So the question is, can we understand basically what governs the sort of arrival time of these ions, the first ions, because that gives information about the type of drag that these ions will experience. Okay, so this is the experimental setup, and these are the kind of results that they have been able to gather. So what they found is that if you calculate the mobility of these trapped ions, then for temperatures greater than 0.7 Kelvin, more or less, you basically have significant drag that the ions experience in comparison to the free negative ions. So these black dots here correspond to experiments for ions not trapped on vortices, and what they see is that below a certain temperature, the mobility drops off very rapidly, which is believed to be associated with the decrease of the roton density. And then at some point, it becomes basically limited by the phonon density in superfluid helium-4. And you can actually do a theoretical calculation to estimate that the inverse mobility should scale as the cubic power of temperature, which can be attributed to the phonon density. Now, in these experiments, what they find is that the mobility is significantly higher, which is, can be explained in terms of perhaps some additional drag force being induced by the interaction of the ion with the vortex. But at very low temperatures, you do collapse onto the mobility of the free ions. Now, I should point out that this type of experiment was studied a long time ago in the 1970s by Ostermeyer and Glaberson. And they basically went down to these temperatures, whereas the Manchester experiments have now pushed this to even lower temperatures using two different samples of helium-4 with different concentration levels of helium-3. And you can see that at some point, helium-3 significantly increases the drag experience because you basically encounter the phase transition temperature for superfluidity of helium-3, where they basically condense onto the vortex cores. So within this temperature range here, what is not clear is what are the main mechanisms that are contributing to the drag force. Now, one of the things I should point out, if you haven't seen these type of plots before, is that in experiments, they like to plot things in terms of the inverse mobility rather than the mobility. And that's simply because if you think of the drag as being contributed by various excitations, so phonons, rotons, thermal waves, and so forth, then it turns out that a good approximation, the inverse mobility can be determined through sort of additive contributions. Okay, so you can just add the different contributions, and it turns out to be a good model to work with. Right, now, as soon as these measurements were made back in the 1970s, actually, people became interested in trying to understand what's happening to the mobility. Why is it the mobility drops very suddenly at this characteristic temperature of around 0.65 Kelvin or thereabouts? And so there were various theories put forward. So I've named a few here. So there's a theory by Fetter, Noguchi, Omi, and Otsui, and there were, I think there's another paper by Douglas and so forth. And the idea there is that they thought these vortices are going to be to have lots of Kelvin waves that are excited due to thermal activation. So thermal excitations are going to excite Kelvin waves, and this is going to lead to enhanced drag that the ion experiences. Now, there is another theory that was put forward by Oguchi, which I'll explain a little bit more about later on in my talk. But basically, the idea of this theory is that when you have a vortex line, you have a velocity field that's induced by the by the vortex. And so that modifies the effective trapping potential for rotons, and there is an enhancement of the roton density around the vortices. And so that basically can contribute to the drag. Now, it's clear when you look at these plots that the roton density at higher temperatures agrees much better than the vortex wave theory proposed by these other authors. And if you pause to think about it, actually, you would think that, well, if you have vortices are activated, but there is significant temperature present in the system, then you're going to have a lot of mutual friction that's acting on these vortices, and that's going to dampen their any excitations that can live on the vortices. So we wouldn't expect too many Kelvin waves to reside at these temperatures, whereas the band roton theory does seem to be a plausible argument. And so one of the things we wanted to understand is, can we basically shed some more light on the qualitative physics of this problem? Okay. So to do this, we performed, we approached the problem using different types of models. And the first thing I'm going to focus on is using essentially like a density functional theory, a rather simple form of a density functional theory. And the starting point is actually to understand in what form the electron resides in the superfluid helium-4. So when you inject electrons in superfluid helium, what happens is that the bare electron experiences the presence of the electrons of the helium atoms. And so due to the Pauli exclusion principle, they basically do not want to sit close to one another. And so it carves out a cavity in liquid helium-4. And so what that means is that these electrons do not reside in sort of the bare state, but they reside in the self-trapped bubble state. And so the typical picture that you should have is that you have some kind of effective wave function or the parameter that describes the superfluid state of helium. And then there is this cavity where the electron wave function sits. And there is some kind of balance of forces that's established that determines the size of this cavity. Now, all of this is inferred through indirect measurements. And basically, the way people arrived at this picture is by noting that the mobility of these negative ions is exceptionally low. And that's because it has a high effective hydrodynamic mass, which is related to the displaced fluid by the electron. Okay, so this is the setup that we have for our system. And so what you end up with is a balance of forces that's established, where basically you have the 0-point energy of the electron that pushes out or carves out the cavity. Then you have some surface tension that's basically trying to collapse the bubble, and you have also the pressure exerted by the surrounding fluid. And so some balance is established between these competing effects that we would like to quantify. So, working sort of in the spirit of what Gross and Clark proposed some time ago, basically the superfluid is going to be modeled in terms of like a mean field description, where basically you have this psi representing some kind of order parameter of the superfluid state with kinetic energy term, some interactions between the bosons or the helium atoms, and then an interaction term between the helium atoms and the electron. And you have a linear Schrodinger equation where you also have interactions between the electron wave function and the helium atoms. Now, in general, these interaction potentials are going to be non-local, and they're going to be rather complicated. And in fact, one can also argue perhaps it's not sufficient to keep only pairwise interactions. Maybe you need also three-body interactions, because the helium is a strongly interacting and correlated system. But for simplicity, we will just work with this model as a starting point, and then make the drastic assumption that we can model everything using S-wave scattering length. So it becomes much more like a Gross-Betayevsky equation that we study. Now, it turns out that one can tune these parameters to match certain properties in experiments. So one of the things that you cannot measure, accurately replicate is the equation of state. So the pressure density relation in helium cannot be correctly represented with this simple model. But what you can get right is, for example, the ratio of the bubble size to the healing length. And this turns out to be an important parameter in the system. And so with this simplification, we end up with this kind of coupled system of equations that we want to solve. And then what one can do is use this equation to estimate the energy of the different contributions of the electron bubble. So the 0-point motion will give you this contribution to from the kinetic energy. You will have essentially an energy contribution associated with carving out the cavity, and then basically a surface tension term. And if we minimize the energy with respect to the spherical bubble radius that's assumed here, then you find that you get this relation where basically for the kind of parameters that you typically encounter in helium, this last term turns out to be not so important, and the main balance turns out to be between these two terms. And so this gives us a way of approximating to good accuracy the bubble size of the electron as a function of the various parameters. And so for the typical experimental conditions, which are carried out at 1 bar, you find that the bubble radius is at equilibrium when you have a size of around 18 or 17 angstrom, thereabouts. Okay? So as I said, we can tune the parameters to get these important length scales out in the problem. Okay, so to proceed now, we basically take this model, we just non-dimensionalize the problem. But in addition, we introduce basically a forcing term in the form of a background uniform electric field that acts on the electron and basically accelerates the electron due to the presence of this field. Now, one of the challenges with solving this equation directly is that the electron mass is much, much smaller than the helium atom mass. And so you have a huge disparity in the time scales that the system can exhibit. And so that means any small changes in the behavior of the surrounding fluid will cause essentially instantaneous changes in the response of the electron. And so the only way to get around this problem and make the computations feasible is to introduce what's called an adiabatic approximation, where you assume that the electron is essentially propagating in the ground state and where the helium is dynamics is resolved explicitly. Okay, now, even with this simplification, it turns out that it's still rather challenging to solve this problem in full 3D setups. And so we, working with my former PhD student, Alberto, we had this basically implemented on graphical processing units. And we used different kind of computational grids. So we used this blue box to simulate the electron wave function, which is localized. We used this long sort of channel here to simulate the superfluid. And then the electron is ensured, and we ensure that the electron stays inside the center of this domain by basically by solving the equations in a moving frame of reference with the electron. Okay, so after doing all of this, we can actually solve the problem in full 3D, which is a significant kind of advance in terms of what has been done before. So, for example, these authors have solved more sophisticated density functional theories, but nevertheless were constrained to work with axisymmetric flows because of the cost of the computations involved. Right, so this is the model that we used, and basically now I'm going to start off by just showing you some results for the free electron initially, to basically just make sure that we can validate the model and demonstrate that it has the correct behavior in terms of the ion-vortex interactions before moving on to try to explain the behavior of experiments. So when we apply the electric field on the ion, it accelerates. And because this is at 0 temperature effectively, it continues to accelerate until it reaches the critical velocity for which vortices are nucleated. So in experiments, you might not achieve this velocity at finite temperature because the velocity might be limited by the scattering of phonons or photons. Now, when you begin to nucleate these vortex rings, the velocity drops drastically, and that's why you see this sudden drop. And in these particular cases, for these values of the very small electric fields, the ion ends up being trapped completely on the nucleated vortex ring. However, for intermediate values of the electric field, what we find is that the ion nucleates a vortex ring, but then it can escape and it can get recaptured, and you get this sort of intermittent behavior, and so you begin to see this kind of oscillations, large-scale oscillations. And for even larger electric fields, the well, basically, it's you have the ratio of the masses, you have the scattering lengths in the model that we've imposed. It's essentially around 17 angstrom for helium. It's around 1 angstrom, the healing length. So, yeah. So for large electric fields, then just to give you sort of an illustration of the type of dynamics that one observes. So, in fact, this is not very large. This is sort of it's intermediate value, shall we say. So you nucleate vortex rings, then you begin to see this sort of leapfrogging behavior that is established, and at some point this breaks the symmetry, and the ion begins to wander and exhibits chaotic behavior in the transverse direction. And so in experiments, of course, what you expect is all of these sort of drift velocities are sort of long-time averages of the dynamics. So you expect that what you're really measuring is the chaotic behavior of the ion over a long period. And so rather than extracting the velocity over this interval, we extract sort of the mean velocity over this interval to try and compare with experiments. For higher electric fields, the situation is even more complicated. So you get basically a turbulent tangle behind the ion. And as before, the symmetry is broken rather quickly, and then you begin to see sort of this wandering around of the ion. And as before, you get this chaotic behavior, from which you can begin to extract the limiting velocity of the ion after a sufficiently long period. Now, what you're seeing here is basically because our channel has periodic boundaries all around the side, so that's why as it sort of drifts out of one side of the channel, it comes back in the other side. That's why it looks a bit funny, the simulations. Okay, so repeating the simulations for various values of the applied field and calculating the drift velocity, we can then basically identify essentially a mobility. And because you see some kind of linear dependence here. Now, at this point, before we go on to compare with experiments, I should say that the mobility is something that has been studied quite extensively in experiments in helium-4. And typically for very low electric fields, there is this initial linear trend here, which is set by the phonon limited mobility, which is always essentially present when you're at finite temperature. Then you begin to nucleate rings, and the velocity drops drastically. And then you begin to enter the second regime where you have vortex nucleation limited mobilities or roton limited mobilities, depending on what pressures you're in. So when it comes to making comparisons, it's these slopes here that we're interested in from experiments and not these ones, which basically do not apply since we're at zero temperature in our models. As I said, we're at zero temperature. We don't have temperature in our models. Yeah, these are experiments, and that's why they have this effect. Okay, so we tried to find some data to compare against, and after sort of digging through the literature, we really found sort of two data sets that seemed to be remotely relevant. So there was this paper in the 1980s where basically they did these experiments and measured the mobility. And this is the numerical value that we obtained, and this is their experimental value, which is off by a factor of 2. But note that the experiment was carried at a pressure of 25 atmospheres. And it turns out, actually, that a pressure of around 10 or 15 atmospheres, the nucleation of vortex rings is essentially replaced by roton emission. And since our model doesn't basically have rotons, we do not expect very good agreement. But luckily, we found another data set, which turned out to be carried out at slightly different conditions. So I think it was around a pressure of 10 bar. And for this data set, the experimental values turned out to be much closer to the numerical simulations, which is consistent with the fact that in these particular experimental parameter regimes, the nucleation is going to be vortex rings rather than protons. So with this basically study, we were able to kind of verify that if the dynamics of the system is governed or dictated by the interaction of the ion with the vortices, so the vortex dynamics that's important, then it's a good model to capture most of the physics. And so with that, we can proceed basically to understand some aspects of the vortex dynamics associated with the mobility of trapped ions. How much time do I have, by the way? 15 minutes, okay. Okay, so now taking this model, what we did is we started off with initial condition of an ion located on a vortex. And because we are forced to use periodic boundary conditions, we had basically an array of 4 vortices here, and we applied an electric field along the axis of the vortex. And so what we observed is that as the ion accelerates, it begins to excite a localized disturbance, and this localized disturbance becomes of large amplitude, sort of soliton-like disturbance, and I'll explain why it's a soliton-like disturbance. But you have essentially this sort of ion soliton complex that arises and basically continues to grow. And of course, in experiments, if you have scattering with thermal excitations, that can basically saturate the growth of the soliton. This kind of behavior can be observed when you're at sufficiently low electric fields, because if you're at higher electric fields, then basically you just snap the ion off the vortices and you get chaos and a tangle basically produced. And so that's not the regime that we believe the experiments are in. Okay. Now, one of the things that's been observed experimentally is that as you vary the electric field, increase the electric field, the drift velocity increases, but then it reaches some point where it saturates, and it's different values depending on whether you're using positive or negative ions. And in our simulations, we observe that as the velocity of the ion increases, it then begins sort of to decay and it seems to approach some kind of plateau. And that seems to be associated with the strong emission of Kelvin waves, or excitation of Kelvin waves, that acts as a channel for dissipating energy from the system. So one of the things we wanted to try and understand is what is this dissipation channel, and can we use this insight obtained from sort of the qualitative behavior of the physics of these simulations to make the connection with what's observed in experiments. Okay, so what we've learned from these simulations is that these soliton excitations can exist. And in fact, if you look at the sort of history of the subjects related to the study of solitons and vortices, then there are 3 key works that emerge. So there is this paper by Hashimoto that basically first recognized that soliton-like excitations can exist in the vortices. And then thereafter, this was essentially confirmed in classical fluid experiments by Hoffinger and Maxworthy in these papers. So one of them is Nature, and I believe the other one is a JFM paper. Okay. Only a few years ago, we were also actually interested in another type of nonlinear excitation that's called a breather, which, unlike the soliton, is a fully time-dependent solution, so it doesn't appear steady in any moving frame of reference. And this has not actually been observed yet in experiments, but the results that we've obtained made us curious whether what we are observing, what was being detected in the experiments is an indication of the presence of soliton excitations. And so this is now what I'm going to try and explore more fully and try to present a theory for that. Right, so the leading order behavior of a vortex line can be described essentially by the local induction approximation, which basically throws all the non-local behaviors of the flow that's induced, and basically just says that you're moving at the local velocity proportional to the local curvature in the binormal direction. And what's interesting about this sort of local induction approximation is that given any curve, you can define a curvature and a torsion for this curve in terms of the Serret-Frenet equations. And using this set of equations, you can then describe a vortex not in terms of its position coordinates, but rather in terms of intrinsic variables, curvature and torsion, and encode these in terms of a complex function, which is this phi that I've introduced here. And so it turns out that the dynamics is governed by a 1D self-focusing nonlinear Schrodinger equation. And of course, we know this equation is integrable and it has soliton solutions. In fact, the soliton solutions just come out to be such profile that many people who work in Bose gases, 1D Bose gases, will be familiar with as just bright soliton solutions. And so that's what it is. But then we can unravel this in terms of a curve in space. And what you get is essentially a depiction of a soliton in 3D on a space curve. So this was done by this, in this work by Hashimoto. And basically, these are the equations that he's obtained for the position coordinates of the soliton. And he characterized the soliton in terms of 3 different parameters, what I call the shape parameter. So if t is greater than 1, you get essentially a hump soliton, a cusp soliton, and a loop soliton, where basically it becomes like a non-single valued function along the principal axis. Now, taking these solutions, what we wanted to see is, can we fit our simulations with these family of Hashimoto solitons, and you just have 2 parameters, essentially. And so the 2 parameters are going to be just the curvature, or the maximum curvature and total torsion. And the red lines here is the analytical solutions taken from Hashimoto, and the parameters have been tweaked, just 2 parameters have been tweaked to see whether they fit the numerical simulations, and you see there is excellent agreement with this fit. Okay, now to understand the physics a little better, at this point now I need to sort of delve a little deeper into the formulation of the problem in terms of the equations of motion for vortices. And this is where it gets a little more technical. But basically, a vortex is, can be described by this essentially force balance that includes inertia, the Magnus force, the drag force, and then the contribution from the electric field that acts on a point-like particle that we're going to model. And if the inertia is negligible, then typically we neglect this term and we get essentially the equations of motion for vortex filaments that we typically use, which is just a first order equation in time. So for simplicity, what we can do is assume that there's no background superfluid flow, there's no normal fluid component, and it turns out that for the temperature ranges we're interested in, this sort of second mutual friction coefficient turns out to be negligible. And so when you introduce these simplifications, the equation of motion that we're interested in comes out to be this form here. So the Biot-Savart or local induction term, a drag term, and then a forcing term. Now the mutual friction term that we've retained basically has been extensively studied, and you see that as you increase or as you decrease the temperature, the roton density is depleted very rapidly. And then you basically have a very low temperatures, mainly contributions from phonons and helium-3 impurities, which, as I said, in the experiments of Manchester, they've been able to vary and study their effect. So what we want to do now is understand what is it that basically excites the ion and provides a channel for dissipating energy. And so if we now focus on the equation of motion for a bubble trapped on a straight vortex, then this bubble will have an inertia term in the describing the motion in the transverse direction to the vortex. We will have a Magnus term, and we will have essentially a restoring force that's induced by the trapping potential of the vortex on the ion. And through some analytical calculations using a GP-type vortex, Parks and Donnelly was able to actually calculate this sort of frequency of the restoring force. So now the idea is that as the ion is accelerated, then if you look at the Doppler-shifted frequency of the Kelvin wave spectrum, then if this matches the natural oscillation frequency that comes out of this equation, then you expect a resonance condition to be satisfied. And when you have a resonance condition, that provides a very effective channel for exciting Kelvin waves and dissipating energy. And if you do the calculations, then in our non-dimensional units, this comes out to be of the order of 0.02. And we compared this with the numerical simulations where we basically calculated the precession frequency of the ion around the soliton. And you see that it initially begins to grow the soliton when omega becomes of the order of the same value, 0.02. And it's the same value whether you're at low electric fields or at high electric fields. It's the same number here. So the onset for the creation of solitons is well described by this mechanism. Now, to understand what's happening further, what we need to also account for is some kind of momentum balance in terms of linear momentum and angular momentum, and that's where it's slightly more complicated than the study of just vortex rings propagating in helium. And the reason we work with these objects, impulse or angular impulse, is because momentum and angular momentum are not very well-defined quantities because they depend on the size of the system, the shape of the boundaries, and so forth. Whereas these terms that you obtain essentially by taking the momentum relation and doing integration by parts and throwing away the boundary terms, basically gives you quantities that depend explicitly on the shape of the vortex and nothing else. And so for a vortex filament, we can write our vorticity field as a line integral along the vortex. And then the rate of change of the linear and angular impulse can actually be shown to have these rather simple forms here. So what's nice is that if you look actually at the literature, so basically you can recover some old results that, for example, have been reviewed in this old paper by Carlo Berenghi. And basically, the equations describing the motion of vortex rings in helium-4 using a similar model have been used to effectively match experimental measurements to high precision. And what I'm showing here, I don't I don't expect you to understand all the details of the equation, but the point is that we can essentially go through the formulation and derive equations of motion, and in the case of vortex rings, we can recover the same results. The importance is that now we can actually generalize this formulation to a Hashimoto soliton, which not only has linear impulse, but has angular impulse. And so we can basically calculate the precession frequency of the vortex, which turns out to be important in explaining the experiments. So this also allows us to predict the kind of scaling behavior of how the soliton grows with time. So it turns out that after an initial linear growth, so when the soliton height becomes of the order of the wavelength, then the soliton undergoes a self-similar growth, which you can see through this sort of power law fit here. And as it grows, the velocity drops off according to these sort of exponents that can be predicted from the theory. Right. Now, the question is, can we explain some observations from experiments? And so, at this point, I should just basically go over some of what's been attempted in the past. So, originally, it was being attempted by, I guess, Ostermeyer and Glaberson, is that if you start accelerating the ion, then as you basically reach the critical velocity for exciting Kelvin waves, this Kelvin waves will provide a channel for dissipating energy, and hence that will set the limiting velocity of the ion. Now, if you go through the calculations and calculate this limiting velocity as a function of temperature, then the theory sits up here, whereas the experiment sits down here. And so there's a factor of 2 difference for experiments that have been carried out sort of 30 years or 40 years apart. So the measurements are, there is a reproducibility in the data, but the theory clearly doesn't agree. So if we now work with these equations of motion, the linear and angular impulse, then basically you're expecting that they're going to be constant in time. The soliton has reached basically the limiting size. And so you can combine these equations to end up with some kind of consistency relation that can be solved, and that will set the shape of the soliton. And if you do that, the shape of the soliton comes out to be to have a value of 0.67, which was in remarkable agreement with the value that we initially just picked by hand just to get a best fit of 0.65. And so the theory can predict the equilibrium configuration of the soliton that we observed in the simulations. To explain the limiting velocity, now what you do is you use a similar kind of equation for an ion, but now the ion is not on a straight vortex, but on a general curved vortex, and so the equation of motion again will have an inertia term, a Magnus term, and a restoring force term, and you assume that the ion basically is sitting on the vortex, but with some displacement vector, because it doesn't need necessarily to follow the vortex. So this allows me to obtain an equation for the displacement vector, and the important point to take away from all of, sort of this discussion here is that what you end up with is a kind of a harmonic oscillator for D, a harmonic-like oscillator for D, but with a forcing term that is set by the fact that the soliton is sitting on an ion, the ion is sitting on a soliton that's presetting at a certain frequency, and so it's experiencing a centripetal acceleration. And so this acceleration basically acts as a forcing term. So there's a frequency associated with this oscillation that's set by the soliton, and there is a natural frequency that will come out from this. And so this provides an ideal candidate for, again, satisfying another resonance condition. If the frequencies of the two match, then what will happen is that the ion will start oscillating very strongly on the vortex and will emit Kelvin waves. Okay? And that's essentially because the inertia of the bubble is different from the inertia of the vortex because they have different effective masses. And so matching the frequency of the soliton that's given here with the frequency that's obtained from a solution of this equation, we obtain the limiting velocity of 12 meters per second, which is in excellent agreement with the measurements that I presented just a slide ago. Okay, and then just to go a little further, so the theory also allows us to predict the temperatures at which the solitons will begin to grow and become, basically start pushing the ion off the central axis of the vortex. So if we tie these results with a theory that was developed actually quite some time ago by Iguchi, which is basically the band roton theory, that says that you have essentially a halo of rotons trapped around the vortex, then you can calculate analytically or semi-analytically the mobility of the ion due to this band rotons, because you can essentially obtain explicit expressions for the energy of the band rotons and the number density of the band rotons. And the basic theory involves some kind of parameter here, they call this of FL, which basically tells you the fraction of rotons that can interact with an ion. And so if you think of the ion as now being displaced off the central axis, then it's in a region where there is less roton density, and so you expect basically enhanced mobility. And so that's what we believe is the mechanism that's basically giving you the enhanced mobility. And if you put all these theories all together, it's a rather elaborate, and I don't want to get into all the details, but the important temperature that comes out is 0.63 Kelvin, which is precisely where you see the data beginning to deviate from the high temperature values, so the benefits that you see at higher temperatures. So we, putting all of this together, we have sort of the GP simulations, the experiments, and the theory, and all the numbers seem to be tying in together, and that's strongly suggestive of the presence of these soliton-like excitations that are being formed in these experiments, and the mobility is basically indicative of their formation. So with that, I'll end with some conclusions. And basically, we have revealed that these soliton-like excitations can form, leading to a soliton-ion complex. What's important is that the sort of centrifugal force that's pulling on the ion as it goes around the vortex pushes it off the center of the vortex, and so basically the drag is minimized due to the rotons, and this leads to the enhanced mobility. And the theory has also been able to provide us some good quantitative agreement with measurements. And for me, what's interesting is that the results basically give a window into the temperature range where experiments, it's useful to do experiments to probe features of superfluid turbulence, because below 0.6 Kelvin, you're going to excite lots of nonlinear soliton-like excitations, high amplitude waves, and so forth. But below 0.3 Kelvin, you're going to be significantly damped by helium-3 that's usually always present. And so there's a very narrow window within which I think experiments need to be conducted to study these other regimes of superfluid turbulence. And so with that, I'll end.